So good morning to you all. I welcome you all to this session. We have our speaker for today, Ramya, with us. And at the outset, I would like to thank her for agreeing to give a talk to you all. She has been working in this field for quite long. So we are looking forward to an interesting talk by her. So let me now hand over to Shivani to introduce Ramya to us.
Uh, Good morning to one and all. It gives me immense pleasure to introduce our speaker today. Ramya Suresh did her graduation and post-graduation in physics from St. Joseph's College. She completed her post-graduation in 2019 and then joined as a project assistant in IISc Bangalore. There, she worked on superconducting qubits and hybrid devices. In April 2020, she joined the graduate school at Purdue University, where she is currently pursuing her studies on superconducting circuits for quantum simulation. So, without further ado, I hand over the session to Ramya Suresh.
Okay. Let me share my screen. Does everyone see my screen?
Yes.
Okay.
It's your screen.
Okay. So, hi everyone. My name is Ramya Suresh. Thank you for introducing me, Shivani. Thank you to Parul ma'am and the physics department at SJC for asking me to do this talk. I was actually quite glad because I was telling Parul ma'am actually 3 years ago, Parul ma'am asked me to present in class. She asked me to learn and present about squids in class, and because of that, I started my studies in this field. That was the first formal entrance of me in this field. And 3 years later, she's asked me to give another talk about squids, but now it's for the current MSc students. So hopefully I've learned a little bit more about squids since the last time, and hopefully I can convey that information to you as much as I can. So let me get started. So today I'll be talking about superconducting quantum systems. And on the screen, you see 3 pictures. And from the top left, going clockwise, these are the quantum processors of Intel, IBM, and Google. So my research area is in superconducting quantum computing, and I will get to this in a little while. But first, I'd like to shortly share background. Shivani has already done a good job. This is my MSc class. I was in the batch 2017 to 2019, and this is my picture perfect class with picture perfect professors, and you can even see Aloysius sir in the back. So I'm really grateful for my teachers and my classmates and everything, because that's where they set a good foundation for me to be where I am right now. So for my MSc thesis, which is done in the second year, and I think you guys also have to do in your second year, I approached Dr. Vibhor Singh at IISc Bangalore in the Department of Physics. He is the PI of the Quantum NEMS lab. And there, so for my master's thesis, I worked on designing, fabricating, and characterizing a superconducting qubit. And after my master's thesis, I stayed on at IISc for another year as a project assistant, and I worked on superconducting qubits, different qubit architectures and circuits. Other people in my lab worked on devices known as optomechanical drums, but I'm not going to be talking about that today. Hybrid devices and etc. And my IISc experience ended with the beginning of the lockdown. So once the lockdown started, I was at home, and instead I was preparing to start my PhD at Purdue University in the US. And my lab here, in the future, we're going to be working on analog quantum simulations, which is using qubits and quantum processors to study analog, like for example, atoms or molecules, study other quantum systems that can't be studied normally or will take extra effort to study normally. Another thing is we will be creating artificial materials. So what is a material? A material is, any material is made out of atoms and molecules that are arranged in a lattice, right? But in my lab, in the future, we're going to create artificial materials, which means we're going to create a lattice of photons, which have particular frequencies and coupling characteristics, and sort of use them to simulate real materials. So that's in the future. That's a little bit about me. So getting to the actual content of the talk, what if I ask you, what is the first thing that comes to your mind if I say the word quantum? As physics students, you might have different answers. And if I was there in person, I would ask someone for their opinion, but since that's not possible, I'll answer the question myself. To me, if somebody asks me what is the first thing that comes to my mind when I hear quantum, I will think of very, very small microscopic things like alpha particles or atoms or molecules. So let's ask the most trustworthy and reliable source of information, Wikipedia, for the definition of quantum mechanics. So quantum mechanics, according to Wikipedia, is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. So for the record, that was sarcastic. Don't take my word for Wikipedia being trustworthy or reliable. You can see that I have highlighted or boxed one particular phrase, at the scale of atoms and subatomic particles. So Wikipedia says also that quantum mechanics is a theory that describes atomic scale physics. And as I said, an atom is the first thing that you might think of. So protons, neutrons, electrons, etc. And then this is justified by other theories that we study in quantum mechanics. For example, we've all studied the hydrogen, or the solution to the hydrogen wave function in quantum mechanics. So quantum mechanics, generally, what most people think of is very, very small microscopic systems. There's an entire aspect of quantum mechanics that most people completely overlook, including Wikipedia, and that is, so I'm going to change the definition here, very low temperatures, so cryogenic temperatures. Quantum mechanics is also applicable to systems that are at very, very low temperatures, systems that are very, very cold. And when we study quantum mechanics at very, very cold temperatures, we can enter the realm, an entire new class of physics phenomenon, macroscopic quantum phenomenon. And the difference between atomic scale and macroscopic quantum phenomenon is that atomic scale is obviously, you have to use a microscope, it's at the microscopic scale. But macroscopic quantum phenomenon are so big, quantum systems are visible to the naked eye. You don't have to use a microscope, you can just see it as it is. Or maybe you might need a magnifying glass, but that's it. So they're very, very visible to the eye. For example, superfluidity. On the very left, you see a picture of superfluid helium. Now, you might have studied that superfluid helium, when liquid helium is cooled below its critical temperature, critical superfluid transition temperature, it attains zero viscosity. And if you have a crucible of liquid helium, then the liquid helium will start to climb up the wall of the crucible and come out of it and drip into the liquid helium reservoir below it. And this will keep happening until every single drop of superfluid liquid helium has exited the crucible and has come out of the crucible, basically. This is only possible because liquid helium because it has zero viscosity. And this is a macroscopic quantum phenomenon. And it just so happens that superfluidity, so the scientists who discovered superfluidity, Peter Kapitsa and John Allen. So they discovered superfluidity, and I have it written down actually. They've discovered superfluidity in 1937, and they were awarded the Nobel Prize in 1978 for it. And so that's superfluidity. The next picture is superconductivity, which I don't think we go through in much detail during MSc. So superconductivity is actually when you cool a metal below its superconducting transition temperature. And what happens is that suddenly this metal has completely zero resistivity. And because of this zero resistivity, there are other effects, parallel effects that happen, one of which is also the Meissner effect, which is what is seen in this picture. So here's a magnet that is levitating on top of this superconductor, because superconducting metals repel all magnetic fields from within. So this is basically like a mirror. The magnetic field is being mirrored and the magnet is floating in its own magnetic field. And this was also awarded the Nobel Prize. So Camerlyn Owens was awarded the Nobel Prize in 1913, I believe, for superconductivity. And another effect, a direct consequence of superconductivity, is the Josephson effect, which is the image on the very right. And I'll be going into a little more detail about the Josephson effect. But the Josephson effect was also awarded the Nobel Prize, I think in 1973. So this is macroscopic quantum phenomenon is a very noble topic, if I could say so. Right, so I want to go into a little more detail about superconductivity and the Josephson effect. So superconductivity is described, or it's characterized by BCS theory, which is Bardeen-Cooper-Schrieffer theory, which, so these three scientists also were awarded the Nobel Prize for BCS theory. So we know that normally a metal, so if you have like a copper block, for example, the copper block is made out of a lattice, a periodic arrangement of copper atoms, and then there are electrons surrounding each copper atom in the lattice. So similarly, when you have a superconducting metal, all you're doing is just you're taking the same block with the same lattice and periodic arrangement, and you're just decreasing the temperature. And what happens when you're decreasing the temperature is that the electrons inside, the electrons, sea of electrons that are inside the metal, they slow down so much, they have such low kinetic energy that they're able to distort the lattice around them, the positive ion lattice around them. So that's what you see in this picture. So you have an electron moving so slowly that the ions, the positive ions in the lattice are attracted to the electron. And because they're attracted to the electron, the entire lattice gets distorted, and another electron is attracted towards this lattice distortion. And effectively what happens is this entire entity of two electrons plus this distorted lattice is called a Cooper pair. So these two electrons, each with half spin, are phononically coupled to each other, and it appears they travel as one entity, and this entity is known as the Cooper pair. And because each electron has half spin, and the spins can either add or subtract, so the net spin of the Cooper pair will be 0 or 1. So the Cooper pair is basically it's a boson. And the restriction for fermions, which are electrons or fermions, half spin particles, is the Pauli exclusion principle. So electrons they always have to follow Pauli's exclusion principle, which says that these electrons cannot occupy the same energy levels or quantum levels. As long as they have different quantum numbers, they can fill up the energy levels. But there's no such exclusion principle for bosons, and because of this, you can have an entire group of bosons that are all at the same energy level, and this is what happens inside a superconducting metal. So this entire all the electrons inside the superconductor form like this a single superfluid of electrons, which all have the same energy levels and all have the same quantum properties and move as one whole entity. And this is what causes superconductivity according to the BCS theory. Now, since the superfluid electrons are actually quantum in nature, they have one quantum wave function associated with them. And because the entire macroscopic system has one wave function, the whole system has one phase, chi, associated with it. So the difference between quantum systems and classical systems is that quantum systems have a net accumulated phase. So the quantum system, the phases of all of the constituent particles of the quantum system will add up and give it a total net phase. Whereas in a classical system, the phases of all the individual particles will cancel each other out, and the net phase of the classical system will be 0. So that's a little bit about, that's BCS theory in a nutshell. Now I'm going to talk about the Josephson effect. So what you see in this picture is a Josephson junction. And Josephson junction is, so basically it is a superconductor, and next to it is a thin layer of an insulating material and another superconductor on the other side of the material. So typically in my lab or in my field, the Josephson junctions we make are made of aluminum. So we deposit a layer of aluminum, and then one side of it, we open it, expose it to air, and the oxygen in the air will instantaneously oxidize the aluminum layer. So it'll have a very thin layer of aluminum oxide on top of it. And then we deposit another layer of aluminum on top of that oxide. So we'll have an aluminum oxide, aluminum Josephson junction. So those are typical Josephson junctions that are fabricated in the lab. But there are different types of Josephson junctions. That's not the only way you can create a Josephson junction. So I'm going to explain how the Josephson junction works. So each superconductor are different quantum systems. So this superconductor is one second, let me use the laser pointer. Right. So this superconductor is completely different than this superconductor, and each of them has a different quantum mechanical wave function associated with them. So each of them have a different phase. Say this one has chi1 and this one has phase chi2. Now, because of the phase difference between these two superconductors, so if the phase difference is chi, the phase difference between these two superconductors causes a potential difference across the two superconductors. So this is, there's nothing, the assumption is that there's nothing connected to the Josephson junction. There are no external voltages or anything. This is just a standalone Josephson junction on its own. But there is still some supercurrent that flows through because these Cooper pairs tunnel through the insulating layer because of this potential difference, which is effectively, it manifests as a voltage. And this is known as the Josephson effect, the existence of the supercurrent, even in the absence of an external potential difference. And the Josephson, the supercurrent is characterized by this equation. I is equal to IC sine chi, where chi is the phase difference between the two superconductors. And IC is called the critical current, which is basically the current when sine chi is 1. It has a much elaborate description that I'm not going to give. So this is the Josephson effect, and there are different kinds of Josephson effect. For example, the DC Josephson effect is when chi is a constant. So when the DC Josephson, when does the DC Josephson effect happen? When there is no external voltage connected, the Cooper pairs just tunnel across, quantum tunnel across this potential. This is like a barrier, a finite barrier. The Cooper pairs just tunnel across to the other superconductor, and since the superconductors themselves are not altered, the state of the superconductor themselves are not altered, the phase difference remains a constant. So sine chi is a constant, and it's basically a DC current flowing through the Josephson junction. This is the DC Josephson effect. But the moment you connect an external voltage to the two ends of the Josephson junction, so for example, if I connect a voltage source, a battery, for example, between here and here, then I'll find that chi varies. So because of this external voltage, the phase of the superconductors will change, and because of this changing phase difference, within the Josephson junction, sine chi is also changing, and therefore I varies sinusoidally with chi. And this is known as the AC Josephson effect. There's also the inverse AC Josephson effect, which happens when you provide an AC voltage source. So in conclusion, that is the Josephson effect. And one small subtle point that I want to make is that a Josephson junction is a nonlinear inductor. So when you invoke the Josephson equations and account for the when you include potential energy in the equation and talk about the relation between current and the phase difference, then you see that there is a cosine term that enters the equation, the relation between the current and the effective inductance of the Josephson junction. And so basically the Josephson junction is a nonlinear inductor. And also because the Josephson junction, this superconductor is a metal, and this superconductor is another metal, and there is a dielectric sandwiched between these two metals. A Josephson junction is also a capacitor in some sort. So because the Josephson junction is both a nonlinear inductor and a capacitor, effectively a Josephson junction is an LC tank circuit. And I'll get to that in later slides, but that's something that might be good to keep in your minds. So Parul ma'am wanted me to talk about SQUIDs, or superconducting quantum interference devices. So what is a SQUID, first of all? This picture I have here is a device known as a DC SQUID, and it is basically a loop of two Josephson junctions. This is one Josephson junction, and this is another Josephson junction, and they're arranged in like a loop manner, and a current is sent into the SQUID and the current exits the SQUID as a whole. And because there are two Josephson junctions, previously we saw that the current through each Josephson junction was IC sine chi. Because there are two Josephson junctions now, the current I will equal IC sine chi 1. So chi 1 is the phase associated with the first Josephson junction, and chi 2 is the phase associated with the second Josephson junction. So I is equal to IC sine chi 1 plus IC sine chi 2. And one aspect that I want to remind you right now is magnetic flux. So you've probably learned from electrodynamics that magnetic flux, threading any loop of area S, is given by, so phi is the magnetic flux, and it is given by the dot product of the magnetic field with the vectorial area. So the vectorial area would be a vector. In this case, it would be pointing out of the screen, and it would have a magnitude equal to the area of this loop. So that's the magnetic flux, as you've probably learned from electrodynamics. Another quantum phenomenon that I want to talk about, however, is magnetic flux quantization. And so what is magnetic flux quantization? It turns out that in a loop of superconducting metal, the flux that is allowed to thread through the loop is always going to be quantized in multiples of this factor known as the magnetic flux quantum, phi naught. And phi naught is defined to be the Planck's constant divided by 2 into the charge of the electron. In superconducting loops, similar to how angular momentum is quantized or spin is quantized, flux threading the loop must always be quantized. And this is what makes the squid so unique, because it exploits magnetic flux quantization. So here in a squid, we don't have a complete superconducting loop. Instead, we have a superconducting loop that is discontinuous at 2 spots, particularly this insulating barrier and this insulating barrier. So because of these discontinuities, we won't have the flux threading the squid won't be exactly multiples of phi naught. Instead, it'll be a factor of phi by phi naught, this factor here. So if we define chi1, that's the phase difference of the first Josephson junction, to be some chi plus pi phi by phi naught, and chi2, that's the phase difference for the second Josephson junction, as some chi minus the same factor pi phi by phi naught. And then substituting this chi1 and chi2, these chi1 and chi2 values inside in this equation, you get I is equal to IC sine chi plus pi phi by phi naught plus IC sine chi minus pi phi by phi naught. And by trigonometric identity, you know that sine A plus B is sine A cos B plus cos A sine B. So using those trigonometric relations, it's possible to simplify the supercurrent going through the squid loop to be IC cos pi phi by phi naught into sine chi. So this is the current that goes through the squid loop. And if you compare it to the same supercurrent equation for the Josephson junction, you see that the only difference is this interference term, which is cos pi phi by phi naught. And otherwise, IC sine chi is the same thing that you see for the Josephson junction, the plain Josephson junction. Now, because of this interference term, this interference term is what makes squids so useful. So you see that the supercurrent through the squid is directly proportional to the magnetic flux that is threading through the loop in the middle. And this magnetic flux can be anything, actually. It depends on the magnetic environment. You can change the environment such that you can tune it to a particular magnetic field that you want, or you can use it to check the magnetic field in reverse. But basically, so the characteristic is such that the voltage, or equivalently the current through the squid loop, is sinusoidally, it varies sinusoidally with phi by phi naught. And so this is known as quantum interference. These are the interference fringes, if you can call them. This is exploited in many areas. So applications of squids. First of all, in materials engineering, if you are manufacturing a material, I think Parul ma'am will be able to elaborate more on this, perhaps, since she works on metallic glasses and might have used a squid magnetometer before. But when you're making a material, you want to study magnetic properties of a material. For example, the material might have very, very small magnetic fields that cannot be measured with any other magnetometers except for squids. So squids are extremely sensitive because so they're extremely sensitive because, I mean, they can be very small, and since this you can change the magnetic flux quantum is very small, so as a fraction you can study whatever magnetic field you want. And if you have a particular material with a very small magnetic field, you can use a squid and try to measure that very, very small magnetic field. So that's its use in materials engineering. And the next application is almost similar, but in the field of medicine. So our brains and our hearts, for example, generate very, very small magnetic fields. And these magnetic fields are usually, you can't measure them using a majority of other magnetometers, but you can use a squid to detect these really, really small magnetic fields and characterize brain diseases or heart diseases, etc. And amongst other applications of squids, the third one I'm going to talk about is quantum computing. So that is the research field that I work in. And if you look at this picture, this is actually a quantum processor that Google and the University of California at Santa Barbara, they worked on together. This is a, I think it's a 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a 9-qubit quantum processor. And if you look really closely, these tiny rectangles down here are each squid loops. So there are 9 squid loops that are placed in an array like that. And so these are some of the applications of squids. If anybody has any questions, please don't hesitate to interrupt me and ask. Just putting it out there. Otherwise, so I would not be able to sleep peacefully at night if I didn't talk about superconducting quantum computing. In this picture, you see a dilution fridge, a dilution refrigerator. And these dilution refrigerators are used to reduce temperatures down to a few millikelvins, so like tens of millikelvins. And what we put at the bottom of these dilution refrigerators are the actual fabricated chips, which contain the qubits. And the reason they have to be at such low temperatures is because they superconduct at very low temperatures in like the Kelvin range, and you decrease the temperature to make sure that there are no extra thermal noises, or we're trying to minimize as much thermal noise as possible. So you decrease the temperature to millikelvin and connect you mount your qubit chips to the bottom of the dilution refrigerator, and then get it down to the low temperature, and it will start behaving quantum, and then you can use it for quantum computing. So why quantum computing? So the CEO of Intel, actually, Gordon Moore, he noted that the number of transistors on IC chips were roughly doubling every 2 years, which means that like for a particular size chip, the number of transistors on it kept increasing or doubling every 2 years because they were improving on the design. So the more, the better enhanced design would have approximately twice as many transistors as the previous design. And he noticed this for many years, from 1971 to 2016. And this empirical law is known as Moore's law. And by 2020, Moore's law predicts that classical computers should stagnate, in the sense that the number of transistors on IC chips cannot grow anymore, because a single transistor will be about the size of one atom. So as of 2018, the smallest transistor size achieved is 1 atom wide. So they've used a single atom to make a transistor. And this is impressive because you can't break an atom, you can't break it any further. It has to stagnate at 1 atom. You can't make it any smaller than that. And also, the size of at atomic scales, as Wikipedia said, quantum effects begin to take over rather than classical physics. So this is why quantum computing is really important, because 2020 is this wonderful year that we're living in, and soon classical computing is probably going to stagnate, and you need something else to improve on computing, which is what quantum computing is going to do. So quantum computing is, you might have heard about qubits in the news, or you may have never heard about it, but like, what is a qubit? A qubit is short for quantum bit, and qubits are the constituent, they are the constituent systems of quantum computers, similar to how bits make up a classical computer. So we all have probably heard that a classical bit is 0 or 1. For example, the switch, like any light switch or fan switch, is the best example of a classical bit. You can have the light on, or you can have it off. You can't have it, you can't balance the switch in between and have the light somewhat on and somewhat off. That's not possible. And so the classical bit is binary in the sense it's either on or off. And for n bits, there are 2 to the power n states. For example, if I have a 2-bit system, so if I have 2 bits that are connected, I can have 0, 0, 0, 1, 1, 0, and 1, 1 as my 4 states. I can use, so I have 4 states for n bits. I have 2 to the power n states. On the other hand, a quantum bit is, for example, if you take the ground state and the first excited state of any atom as your 2-level system, so one you can define as the on state and one as the off state, or 0 state and 1 state, then this would be a perfect example of a quantum bit, because, for example, when this electron jumps from the excited state to the ground state, and by emitting a photon of a characteristic frequency, it is effectively moving from 1 state to the 0 state. And because of its quantum nature, in an ensemble of such qubits, or an ensemble of such 2-level systems, you won't know exactly, you don't need an ensemble as of such. Even in a single system, even in a single quantum system, you won't know exactly whether the electron is in the excited state or the ground state at any given time. There is a certain probability that the electron will be in an excited state or in the ground state, but you can't be sure. So this is known as a superposition. So the state of the electron is actually a superposition of the 0th state and the 1 state. So it is in some probability of being in the 0th state and some other probability of being in the 1 state. And this is a perfect example of a qubit. For n qubits, there are 2 to the power n superpositions. So if I have a 2-qubit system, then my wave function will be A00 plus B01 plus C10 plus D11. Now that is a single superposition. That's a single wave function. That is a single state. And that means that effectively, if I have an n-qubit system, I can put it in a superposition. I can put all these qubits in a superposition, and effectively I'll have the equivalent of 2 to the power n bits. And clearly, this is an advantage over classical computing, because you're getting more out of less number of bits or qubits. So to illustrate this further, I'm going to talk a little bit about search algorithms. So you might have heard of Grover's search algorithm. If you've not, generally for search algorithms, so for example, a search algorithm is something that you would use to search for a particular correct answer amongst a list of possible answers. So if I have a 2-qubit system, then a 2-qubit or a 2-bit system, then possible answers could be 00, 01, 10, or 11. Now in a classical computer, you would have to change your system to 00 and then ask the computer, is 00 the right answer? And in the worst case scenario, it will say no. Then you will change the system again and you'll change it to 0, 1. And then you'll ask the computer again, is 0, 1 the right answer? And in the worst case scenario, it'll say no. Next, you'll ask it about if 1, 0 is the right answer. And if it says no, then you'll ask if 1, 1 is the right answer. And if the 3 answers above are all wrong, then 1, 1 has to be the right answer. So at maximum, it takes 4 tries to find the correct answer on a classical computer. But on a quantum computer, you can immediately put your 2 qubits in a superposition. So this is the superposition. The wave function is 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Obviously not normalized. And then you ask the quantum computer which option gives a positive result. So which one, which superposition state, which state from the superposition is giving me a positive result. So like which is it's asking the quantum computer to choose. So at maximum, you need only 1 try in this case, and the quantum computer will give you the right answer in 1 try. So that is a clear advantage over a classical computer. But this is more of the computer science side or the computational side of quantum computing. I'm actually in the I work on the hardware part of quantum computing, if I can say so. And it basically deals with creating superconducting qubits, fabricating superconducting qubits, and then using those superconducting qubits for quantum simulations or quantum computing, etc. And I keep saying qubit, so what actually is a qubit? So I told you that a qubit is like a 2-level atom, you can take 2 levels of an atom to be a qubit. But what we do in superconducting quantum computing is we create artificial atoms. Why do we do this? Because isolating a single atom is very difficult. You would have to use a lot of precaution to take only 1 atom and then make sure that it's in a position where you can modify it or use it for quantum. You can send it pulses, you can send it different signals and modify its response, etc. So instead, in superconducting quantum computing, we make artificial atoms, and these artificial atoms are exactly identical to real atoms everywhere in a quantum mechanical manner, except that they're much larger. They're actually visible to the naked eye, these artificial atoms. And because we are engineering them ourselves, we can modify them according to our needs. So we can make any atom. We can engineer any atom we want, a hydrogen or helium, iron, lithium, anything. We can, if we tweak the energy parameters, we can create any atom that we want. Now, how are these artificial atoms made? If you recall, I told you that a Josephson junction is really an LC tank oscillator. So this is a Josephson junction, and it's equivalent to this nonlinear LC oscillator. This symbol here is a nonlinear inductor. It represents a nonlinear inductor. So this is really just a nonlinear LC oscillator. And another thing is that the squid, which is made of 2 Josephson junctions, will obviously also have to be a nonlinear LC oscillator, but now it's tunable because we can use an external magnet or like an electromagnet or a small bar magnet, any magnetic field, to tune the energy parameters of this entire LC tank circuit such that we get a tunable LC nonlinear oscillator. So Josephson junctions and squids are actually used as artificial atoms in superconducting quantum computing. So this is a typical picture on the right-hand side. It's a very common picture of a superconducting qubit. So, okay, so superconducting, so the qubit is usually just a squid loop with another capacitor, and the capacitor is sort of built around the squid loop such that the capacitance is it behaves as like a capacitor in series with the squid, as a gate capacitance. And so this is the artificial atom as of such, and this picture is so here's the artificial atom, the green thing, the green square here, which the arrow is pointing to, and the surrounding circuitry is basically the readout mechanism for reading out the state of the qubit. I'm not going to go into details about readout mechanisms, but so basically the squid is being used as the artificial atom, and this is how qubits are being made in using superconducting circuits. This is a picture of superconducting. This is a chip, a superconducting circuit chip. And here, these colored plus shapes are each the capacitors, the gate capacitors that I was talking about. And if you look really closely, you can see that there is a tiny squid loop at the bottom of each of these plus shapes. And it's the squid loop plus these capacitors, which is the artificial atom. So in this circuit, there are 5 artificial atoms. So this can simulate any 5 atom system that you want. You can simulate a pentatomic molecule, or a pentatomic lattice, or anything that you want using this circuit. What you would do is just tune each qubit to a particular energy level that corresponds to the real molecule, and then you would be able to simulate the real molecule using this artificial molecule that you see on the screen. And it's plus shaped because each of these arms is used for a different control. So the arm on top is used for readout. The arm on the left is used for exciting it to the first excited state. And the right side arms and the arms in between are used for coupling between the different atoms and such. So this is, if you look under a microscope, this is what a superconducting circuit chip will look like. And what you do with the superconducting chip is then you mount it at the bottom of a dilution refrigerator. So if you look closely, each of these boxes is presumably a superconducting chip, which contains qubits and readout mechanisms and control lines, etc. And they're all interconnected at the bottom of a dilution refrigerator and closed. So this is essentially a quantum computer. So with that, I'd like to finish up by saying that quantum computing is right now in the same stage as classical computing back in 1943. So on the right, you see a picture of the Colossus, which was it was a pioneering effort for classical computers back in 1943, and it took up an entire room. And on the left, you see the IBM quantum computers, which are equally as large, if not larger. And this is in present day, so quantum computing still has a long way to go, and it's soon to take over classical computing. And with that, I end my talk. So thank you for your attention. If you have any questions or you want to talk to me, my email address is on the slide. It's a relatively simple email address. You can't forget it. Ramya Suresh 1234556@gmail.com. So thank you.
Thank you, Ramya, for such an amazing talk. I'm sure all of us have learned a lot about supercomputing, superconductivity, and quantum computing. We have a question in the chat box from Amoga Varsha, who asks, how does the loops of qubit work?
I'm sorry.
We
I'm not able to
this.
see the chat box.
Oh, okay. So
Okay.
the question is, how does the loops of qubits work?
Amoga, can you elaborate? Loops of qubits?
Amoga, you can unmute yourself.
Question.
Amoga, you can unmute yourself and ask it. Ask
Hello.
your question. Yeah, go ahead.
Am I audible?
Yes,
Yeah,
please.
hi.
Hi. Hello. We're showing the quantum computation using the qubits, right? Means you said something like there is some kind of loops working. Means the computation working on the loops made of qubits.
Uh, so I said squid loops are used in superconducting qubits. So squid loops, I said squid loops because it's a loop containing two Josephson junctions. And these squids are used at the bottom of these qubits on the screen. So there's no loop of qubit as of such. I was referring to the loop of the squid in the qubit. Does that answer your question?
Yes. Yes. Thank you.
No problem.
Any other questions that anyone would like to ask? You can unmute yourself and ask your question. All right.
So, Ramya,
Mhm.
you were talking about the qubits, the quantum computing, and you said that it saves time because instead of running a classical computer 4 times, you are just running it once, and you know your answer of a yes or no.
Yeah.
So, does it also save your space on the board?
On the IC board?
Yes,
Mhm.
yes.
So right now, quantum computers are not constructed on ICs. Rather, they're constructed on like separate chips, and the chips are relatively large because they need to be mounted in certain boxes, and then the boxes need to be arranged below the computer. So size-wise, it's not. And I mean, that's why the quantum computer, the IBM quantum computer is so big, because size-wise, quantum computing still needs to go a bit of a way, but efficiency-wise, quantum supremacy, whether quantum supremacy has been achieved or not, was a debate between IBM and Google, but it has been achieved now, so
Okay.
it's on its way. Yeah.
Right. Okay.
Any other questions from anyone else? Okay. So I guess we can conclude now. Ramya, I thank you again on behalf of Physeeksee and the entire physics department of PG. I thank you for your time, and it's been a hard time for all of us, but I appreciate you taking our time for us and preparing this wonderful presentation. And I'm sure all of us will go back and read about quantum computing and perhaps pick up our research topics and our thesis topics there. So thank you for inspiring us. And yeah, Paul ma'am,
Yes,
can
yes. So, I must say it's not an easy topic to talk, as all of you would have noticed. She's gone from right from quantum to she's gone to solid state, trying to explain you superconductors and Josephson junctions, and from there to quantum computing. It's definitely not an easy topic to convey to people who've just joined in MSc in an hour. So, as I think Vikrant rightly said, it's basically giving sparking your brain to go back and read and understand what Ramya has been talking about. So it's definitely not easy for first years to completely understand what Ramya has spoken, but I'm sure that it has sparked all of you to
I think it's laid a very good foundation for us first years to
yes.
make sure that when we come to this topic, we understand a little better than the first
Absolutely,
time.
absolutely. And it has also opened up a new area for all you guys, to think that this can also be done. Not many people in MSc think of taking this as a research field. So I must appreciate Ramya for putting all of this together in such a coherent manner for an hour's talk. So it's really
Thank
nice,
you
Ramya.
so much, ma'am, and thank you, Vikrant. If you guys have any questions, I will be happy to answer your emails or answer your questions right now or anything in
Yeah.
the future.
I think even about doing research abroad or working under Vibhokar at IASC, if you guys have questions, you can write to Ramya. So thank you so much, Ramya, for making the session so interesting for us.
Thank you, ma'am.
Yeah.